Okay, welcome. This is my first day here. Yes, so I want to continue a bit along the lines of the previous talk, and at some point I'm gonna diverge. And what I want to tell you about is a series of 3 papers. 2 of them are already on the archive, and one is supposed to be there on Monday. Let's see. This is with Gabriel. Let's see if we make it on time, given all the temptations of Florence. So let's start with motivation. Um, the big motivation for us is a theory challenge of studying thermalization dynamics of closed quantum systems. And this is highly relevant for ultra-realistic nuclear collisions at RIG and LHC, as you have heard from Michal and many other talks in this workshop. But it's also relevant for ultra-cold atom experiments, and I'm not sure if there was a single talk about it here in this program. And this one is a bit to some degree about it. It's not a controversial statement, I think, to say that theory targets specific parametric regimes, such as strong or weak coupling, and each regime has its own language. So strong coupling has this language of holography, black holes, quasi-normal modes. Weak coupling has a language of kinetic theory, moment equations, etc. And I believe this fact that there are these 2 languages creates novel opportunities related to the fact that these communities interact with each other in a limited capacity. And in particular, this allows to try to seek for phenomena known from one language in the other language and vice versa. And this talk is precisely about this kind of novel connections and perspectives between strongly coupled phenomena and weakly coupled phenomena. And what Michal talked about in the previous talk, and what you heard before from Jean-Paul Blaiseau as well, is about the hydrodynamic attractor, which on the space-time picture of nuclear collisions arises somewhere here. But it turns out that in the weakly coupled picture of ultra-realistic nuclear collisions, there is another attractor called the non-thermal attractor, also known as non-thermal fixed point, that manifests itself at very early times when the system is anomalously weakly interacting, at least like it was observed in such cases. So it's not really in its pristine form directly relevant for the current phenomenology of nuclear collisions, but it's there for ultra-realistic nuclear collisions for accelerators that, I don't know, would be maybe a size of a solar system or something like this, right? But it's interesting because it can be realized in ultra-cold atoms, and therefore it's something that is directly accessible. And I have known about its existence for already 12 years, but I only got actively interested in it as a research topic because in 2020 we published a review article with Jürgen Vergas and Raju Venugopalan, who actually actively contributed to the study of this non-thermal attractor, and this is somehow how it triggered my interest. And before I go to the technical part of this talk, together with, in particular with Michal, we are organizing also in Italy, in Trento, between 22nd of September and 26th of September, so in about 5 months, another workshop that is entirely devoted to studies of attractors, both in ultra-realistic nuclear collisions and in cold atom physics. The registration is supposed to start in July, so if you're interested in this topic, it would be great to have many of you there in Trento. So let me start with non-thermal fixed point. So in this very weak coupling picture of nuclear collisions, the initial state right after 2 highly boosted nuclei pass through each other is an overoccupied state of gluons, so that there's going to be a range of momenta in which the number of gluons is going to be much larger than there would be for a thermal distribution at the same energy density. What people typically consider is basically a step function type initial condition. And ab initio simulations showed that after a while, starting with such an initial condition, what you encountered is a self-similar situation in time, in which the distribution function in the context of the Bjorken flow, there will be a function of transverse Bjorken flow with rotational symmetry and homogeneity in transverse plane. The distribution function that normally would be a function of time, proper time, Bjorken proper time, the transverse momentum and longitudinal momentum is no longer a function of three functions, but actually becomes a product of a function of one variable that is a pure power law and a function of two variables that are also scaling. And let me just finish this thought. So as a result, like in the scaling regime, you don't have to solve the Boltzmann equation for the dynamics, or you don't have to really solve whatever these people were using, so these classical statistical simulations to solve for the dynamics. If you know in the scaling regime, the profile of the distribution function as a function of transverse momentum and longitudinal momentum at one instance of time, you're gonna be able to get one at another later time simply by rescaling the overall amplitude and the arguments of the function by the respective powers of time. So that's sort of like the simplicity associated with the scaling. And this is called an attractor because starting from different initial conditions, as long as you're overoccupied, you seem to be landing on this kind of a behavior where this Fs is some particular function of two variables that is determined by the QCD machinery, by the QCD kinetic theory, or by this classical statistical approach to QCD dynamics. Lorenzo. So I feel like what people really do is like they solve classical Yang-Mills equation, and this is this classical statistical theory. But then like what they do is they average over different classical solutions. Each solution is inhomogeneous, and it's really a solution in 3+1 dimensions. I mean 2+1 if you have boost invariance, right? But then after averaging, like they average in such a way that everything reduces to the pure homogeneous Bjorken flow. So yeah, I think your intuition is correct. Like this is how you can think about it. Yeah. And this scaling is something that you can really see. So so what this plot shows, taken from the original papers that are already 12-year-old, shows a profile of the distribution function at a particular value of transverse momentum as a function of longitudinal momentum um, at different instances of time. And what you see here is that although like this is just a simulation, these are just numerical data coming from ab initio solution. You can, if you rescale them with the appropriate power, all of these things fall up to numerical errors onto a single curve, right? So indeed, this plot from 2013 indicates that indeed this scaling behavior seems to be realized for SU2 QCD at least, where they took SU2 because of being cheaper than SU3, numerically cheaper. And then this was done using this classical simulations. You can also do kinetic theory simulations, coming back to your question. So this was done 5 years later by Jürgen Berges and Alexas Maziljauskas. And they're like, they just took kinetic theory of QCD. They plug something that looked like this as an initial condition, and they let it run. And over here, what you see is the evaluation of these scaling exponents, and indeed, like they seem to be going at late times. I mean, like this is time in a logarithmic scale in some units to the values, roughly to the values that are consistent with this analysis. So yeah, I'm like the scaling behavior seems to be realized in QCD, albeit for very weak coupling. I mean, I think over here, yeah, the G Young Mills is 10 to minus 3, so it's an extremely small coupling. So in my talk, I will adopt several simplifications. So what we want to do, what I want to do is to understand better non-thermal fixed point, and in particular, I want to understand better how non-thermal fixed points are approached. So Birkenflow is already an additional, perhaps unnecessary difficulty from the point of view of this quest, because the physics depends on, I mean, if you adopt the kinetic theory description, the physics is a physics of distribution functions that are functions of 3 variables, and that's already quite a lot. And what I'm going to do, therefore, is to assume that there is no expansion and the dynamics is just in Minkowski space in flat coordinates, manifesting themselves as a dependence on Minkowski space time, not proper time of Birkenflow, but just Minkowski space lab frame time. And the distribution functions that I will be analyzing in the rest of the talk are the distribution functions that are isotropic. So they are just functions of time and the magnitude of particle momentum. And in this situation, the non-thermal fixed point has only 2 scaling exponents. So there is a scaling exponent associated with an overall amplitude, and there is a scaling exponent associated with the momentum sitting under the distribution function. So that's a simplification because we go from 3 scaling exponents to 2 scaling exponents. And for simulations, we don't have to do simulations where the distribution function at each time step is a function of 2 momenta, it's a function of 1 momentum variable. It's simpler. And regarding what is the input, what is the output? So the input here in this analysis is weak coupling and overoccupied initial state, so that the distribution function at LE times, at the initial time, and somewhat later times is much bigger over some momentum regime than would be equilibrium distribution function at the same energy density. And the outcome of this coming from ab initio simulations, so like from solving kinetic theory equations numerically, as well as from cold atom experiments, show a prolonged self-similar evolution in time. So that this F, after a while, is going to settle on the scaling form where A and B approximately take this form. And there's an observation that goes to the core of this discussion that should be apparent to many of you, but didn't seem to be apparent to the authors who pursued non-thermal fixed points at the beginning, which is that we talk about self-similar behaviors, and self-similar behaviors, these are just power laws that you know, for example, from critical phenomena, and such self-similarity has fixed points, right? Has points of special importance. And these are the points for us that, of course, like t equals trf, but that's not that interesting. The ones that are interesting is t equals 0 and t going to infinity, right? Depending on the value of the scaling exponents, these points are going to be either mapped to each other or I'm like 0 to 0 and infinity to infinity, or interchangeably mapped to each other, 0 to infinity, infinity to 0, right? So these points are kind of special. Nevertheless, like in the scaling phenomena, t that appears in these expressions is just like some t that somebody chose to use. For example, I say, okay, I mean now it's 0 on my watch. Like this is the time variable that I'm going to be using in modeling, non-thermal fixed point on a computer, right? Or maybe you take t as the initial time of your simulation. So there's like something really fishy going on here, that you talk about scaling in a time variable where the origin of time is chosen rather arbitrarily, whereas like from the point of view of the scaling phenomenon, like the origin of time should play somehow a special role, right? So this is something that I would like you to ask to keep in mind, because it's going to be essential for later on. Good. Any questions, comments, thoughts? Okay, so that was the first ingredient of my talk, non-thermal fixed points. And I will be talking about them over and over again because I'm not sure how familiar you are with them. I wasn't until recently. I want to introduce the other ingredient, which are quasi-normal modes. And this is a topic that probably I don't really have to introduce here, but let me give it a try anyway. So of course, like if we start with some PDE, say a wave equation in a cavity, and we introduce, say, Dirichlet boundary conditions at the boundaries of this cavity, which defines the cavity in the first place, then we can seek for a spectrum of normal modes, and this is something that everybody knows from undergrad physics. And if excited, these normal modes, what they do is just oscillate. And if there is an interesting physics, this interesting physics comes from interference between these modes. So like the amplitude of each mode is always constant, right? Like the only thing that changes is basically the phase. But of course, like an important topic of research in the context of relativistic hydrodynamics have been quasinormal modes. And quasinormal modes are the modes in which the eigenfrequencies come out complex. And there are two options to get complex frequencies associated with quasinormal modes. One option is that the equation breaks time symmetry explicitly. So a paradigmatic example for us could be a diffusion equation. I mean, diffusion equation you get as an approximation of the shear channel dynamics or charge diffusion in hydrodynamics. And of course, like if you take this diffusion equation and consider it on a line and do the Fourier analysis, then you get a quasi-normal mode frequency that is proportional to k squared. Overall factor is minus I in this conversion, and D is the diffusivity, right? So this shows that like when we start with some signal, this signal is gonna be decaying with time. And there's a second option over here, which is that the boundary condition makes the problem non-Hermitian. And this is precisely what happens in the context of black hole physics. So black hole horizon acts as a one-way membrane, and this breaks time reversal symmetry, and this gives rise to a tower of quasi-normal modes that you know from holography, but you also know them, at least like the lowest lying one, from LIGO type physics for astrophysical black holes. And if excited, quasi-normal modes decay in time explicitly, right? So after a while, there should be gone from the analysis, possibly apart from the lowest lying one, and often also oscillate. And because of work by various luminaries, including our own Pavel here in the audience, we know that quasi-normal modes are extremely important in holography. So this is the picture of the quasi-normal mode spectrum that basically reproduces what appeared 20 years ago in this paper by Pavel and Andrei Starinets. And what we see here is what they called, or what is called now, a Christmas tree structure. So this is the sound wave channel for say n equal 4 superangular theory. And what we see is like infinitely many short-lived modes that are decaying over a timescale set by the local temperature, and then a few long-lived modes that are intrinsically connected to the properties of linearized hydrodynamic equations. And of course, like the third ingredient for my talk is relativistic hydrodynamics. So if you look at these modes in detail, of course, like these modes are plotted here for a particular value of the spatial momentum, but you can vary this momentum. It's a knob in your system. And indeed, like if you look at how the hydrodynamic mode moves on the complex frequency plane as a function of complex momentum, then from this dispersion relation, you're gonna start seeing familiar features like the if you look at this Taylor expansion in low powers momentum, what you're gonna see is the speed of sound, so 1 over square root of 3 for n equal to 4 superang mils, as well as the ratio of the shear viscosity to entropy density at the q squared. And well, the important take home that everybody knows about is that in this case, the shear viscosity describes the dominant dissipative effect. And of course, like one question that you can take from it is that the reason for the origin of relativistic hydrodynamics near equilibrium is that energy and momentum are just conserved charges. So if you excite energy, is not that it can just dissipate very, very quickly. The way to dissipate energy is actually to transport it throughout the system, until the system reaches new equilibrium. So, imagine that one starts with a non-thermal fixed point and you excite it. That is like you put some energy excess somewhere and maybe energy deficit somewhere else. You should also, these are conserved charges, like you should not expect it to, go away arbitrarily quickly. The question that you can ask, is there a notion of a sound wave propagating on top of a non-thermal fixed point? And the answer, obviously, later in the talk is going to prove to be affirmative. Yeah. And of course, like these concepts that I'm discussing are not, abstract. They leave a direct imprint on the dynamics of quantum field theories that you can observe, and hopefully they also leave an imprint on the microscopic dynamics of heavy ion collisions, but that we don't know for sure because we only operate at the level of models. So, but if you look at holography, this is a plot taken from an old paper on mine. What you can see is that indeed, like in thermalization process, you see a hydrodynamic mode emerging at late enough time, and then what you see is a contribution coming from transient quasinormal modes. So sort of like the take-home message from here is that if you look at how equilibration occurs at strong coupling, you see that quasinormal modes, both the transient ones as well as hydrodynamic ones, play a visible and important role. So sort of what I would like to do with this talk is to try to understand what role quasinormal modes play for non-thermal fixed points. So like the first point of entry for this business would be to understand if non-thermal fixed points have quasinormal modes in the first place, right? Yes. Yeah, I honestly speaking, I don't know. No, I mean it's an interesting question. Although I should say that the sound waves that I would have in mind regarding their propagation would be the ones that would propagate along the isotropic situations. So this would not be the relevant point. Yeah. I mean, honestly speaking, it's a pretty straightforward technical exercise to perform such a calculation. I'm not sure what to expect. Indeed, like you break isotropy, but I don't have like a great feeling what to expect. Yeah, of course. Yeah, this slide. Yeah. Yes. 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 No, no, no. So in ADS-CFT, the only like they don't seem to be any constraints in getting negative pressures. I mean, I don't know if you can get arbitrarily negative pressure. I mean, I think that's a mathematical question. I don't necessarily know answer to it. The fact that they all start at the same point is hidden bias in the initial conditions that we considered. In principle, you can imagine that like these some three initial conditions like would start at different points at t equals 0. What I should say is that there seems to be some microscopic self-consistency condition around the behavior at tau equals 0, such that the starting points could be only discretely spaced. Like not anything could fly, because otherwise you seem to be getting naked singularity in the gravity description, and that's never good. But other than this, like there are various points to consider. It's different than kinetic theory. Yeah. Anything else? Okay. Good. So let's do non-thermal fixed points. So the setup that I'll be using from now on is relativistic isotropic kinetic theory. So we're going to have the Boltzmann equation that we'll be dealing with. On the left-hand side, we're going to have a partial derivative of the distribution function with respect to time. On the right-hand side, we will have a collision kernel. And the collision kernel is the thing that's going to capture the microscopics of your weakly coupled theory. One example, just to illustrate how things look like, a special example is the Fokker-Planck approximation here to the QCD collision kernel, in which case the form of the collision kernel is the following. There's going to be a little assumption that you can, or simplification that you can ask me later about, which is that one particular term here that exhibits an additional dependence on the distribution function, I'm going to just set to a constant, but that's like just a minor technicality. And the important thing is that if you start with this equation as an initial value problem, for example, for this collision kernel, what you're gonna see is that overoccupied initial conditions are gonna trigger a direct cascade, so a cascade in the direction of the ultraviolet. That's gonna be self-similar, that's gonna be the non-thermal fixed point in question. Yes? Because it's like a small angle approximation. So like some integrals you can execute because of this approximation, and that's like a reduction of the 2-to-2 scattering. Well, I'm like I don't remember like all the fine steps of the derivation, but actually my PhD students sat on it for some technical reasons, and indeed starting from the full 2-to-2 scattering after many steps, you end up with this. Yeah. Yeah. I mean, something that I consider part of the standard knowledge, so I never really delve into it very, very deeply. Yeah. Anything else? Yeah. But maybe like to build on this point, I'm displaying this because this kernel actually is way easier to work with than the full 2-to-2 scattering kernel. It has way less integrals. In particular, it doesn't have this angular nasty integrals. So some of the results that are new results in the context of non-thermal fixed points will be derived precisely for this kernel because of the technical simplification that it induces. Yeah, good. So the point of departure for the technical part of this talk is that in a paper that I already displayed in 2018, Jürgen Berges and Alexis Malziaskas made a point that before the actual scaling behavior settles, it might be possible that something similar or appears, but with scaling exponents that are slowly varying functions of time. So that the scaling exponents for non-thermal fixed points are supposed to be constant, right? But now the idea that they pursued is that perhaps it makes sense for the scaling exponents to be slowly varying functions of time. And the intuition for the correctness of this assertion was coming from relativistic hydrodynamics. That's why I'm saying this. Like they wanted to have some notion of like a slow evolution before non-thermal fixed point is approached. And when I get to the relativistic hydrodynamic part of my talk, you'll see that that's not really what's going on. Like that was not necessarily the intuition that was. I mean, this intuition was fruitful, but I'm not sure if it was 100% correct. And indeed, like in their analysis, they look at this expanding situation. They see that they can define a notion of a time-dependent scaling exponent, and that like this notion, it seems to make sense much earlier than this scaling exponent settle on the values that you sort of believe in are constant, right? So indeed, somehow like this time-dependent scaling exponents, are not an unreasonable thing to consider, and this is interesting. Both for theory and experiment, since it makes scaling visible much earlier. And in these experiments that people do with cold atoms, they don't have a possibility to keep the cold atom gas for forever in the conditions. that they want to have. Like they just only have some finite window, like maybe milliseconds, maybe seconds, over which they can do the measurements, and then then it's gone. Like then you have maybe finite size effects, maybe you have like some environmental effects, etc. So if you can see these scaling phenomena at earlier times, that's for the better, right? Because that allows you to see more in the course of the trustability of your experiment. So that's kind of a big deal for this. And what I want to do is to provide you with a very simple reason for this time-dependent scaling exponent. And as you will see, like it's really a triviality, but it's an interesting triviality that originates. And by doing this, I also want to understand a bit how to derive non-thermal fixed point from the underlying dynamics. So the first observation in the kinetic theory regime is that if we have this over-occupation, so that the distribution function has a huge amplitude, then this leads to a possibility that the collision kernel is going to simplify. So collision kernel typically is a rather complicated expression with different powers of the distribution function. But if the distribution function has a very large amplitude, it's going to be the terms with the highest power of f of the distribution function that's going to dominate the collision kernel. And as a result, what might happen is that if you assume the scaling ansatz for your distribution function, it might be possible for your collision kernel to be a homogeneous functional of time, so that in the end, from the collision kernel, you can factor out some well-defined power of this amplitude, overall amplitude A, and the thing with which you rescale your spatial momentum. So that's something that we know happens for particular collision kernel, but it's not always the case. As you've seen, I neglected one term in the Fokker-Planck QCD kinetic theory. So that's like one part of the story. And the second part of the story is that this overoccupation leads to most of the energy or most of the particle number to lie, in some particular range of momenta. But simplified kernel, simplification of the kernel, in principle alters conservation properties. So conservation properties we want to input by hand. And if you impose that the energy is conserved on a non-thermal fixed point, or a particle number is conserved on a non-thermal fixed point, what this implies is that A and B are no longer independent, but actually they are related in a parallel manner, either with a power of 4 for energy or a power of 3 for particle number. So at the bottom of the slide, you no longer have Fs, A, and B. You only have Fs and B or A. I'm like B and A are no longer independent. So if you look at the Fokker-Planck kinetic theory, you will see here that, this is the structure of the kernel. There are these integral expressions IA, IB. This expression IB is linear in F, so there is no simplification that you can do. But now we assume like very high value of F. So in IA, there is the structure F times 1 plus F. So this one over here is negligible when F is very big. So IA becomes quadratic in F. And then IA is multiplied by another power of F, right? And IB is linear in F. And here we have exactly the structure F, 1 plus F. So this one is negligible, right? And this term we replace by F squared, right? So this is kind of a simplification of the kernel that we have in mind. And what this shows is that for the elastic scattering described by Fokker-Planck equation, this power kappa is equal to 3. So this kappa is going to be the power, the overall power that we can factor out. Sorry, the overall power of F that appears in the collision kernel, right? So we see indeed that the over-occupation simplifies significantly the collision kernel because some terms are literally dropped from it. And because of this, yeah, because of this f appearing in a particular power, we can pull this trick. And when we roll with it further, it turns out that the Boltzmann equation actually factorizes into two equations. So by the virtue of separation of variables that you know from undergrad physics. So on the left-hand side, what you have is an equation that governs the time dependence. On the right-hand side, there's an equation that governs the shape of the distribution function in the scaling regime, right? So what this shows is that non-thermal fixed points are not very like mysterious phenomena that were always to me when I started looking into them, but actually like they follow very directly from the Boltzmann equation if you assume overoccupation and conservation of energy or particle number. And as a result of this, what happens is that the Boltzmann equation, at least for some collision kernels that are important, factorizes into equation that governs the time dependence and an equation that governs the momentum dependence. And that's something that does not always occur. For example, it doesn't occur for Bjorken dynamics in the equilibration processes, right? Like this is something that requires this overoccupation assumption in the first place. And this shows that non-thermal fixed points are about vast reduction of complexity in the sense of dimensionality reduction that the time dependence and momentum dependence factorize. Like they are sort of two things that happen in parallel. And of course, what one can do is one can solve the relevant differential equation. I mean, this one is extremely easy to solve. This one is much harder to solve. And when you solve this equation, what you're gonna find out is that the solution of this equation is gonna be the B of t, that is precisely this power law that we are after. But there is like one little change that occurs, which is that the integration constant associated with this differential equation picks an offset in the time variable. So it's not like a power law in t, but it's a power law in t minus offset. Sorry? D1 is a constant, yes. D1 you can think of as setting the overall amplitude of the scaling function, or this Tref in this expression, yeah. The question is what T star is, of course. So from this point of view, T star is just an integration constant, right? That you get when you solve this equation in full generality, right? But what it really gives you is an offset in time. And remember what I told you earlier, that in scaling phenomena, the origin of time matters. And what seems to be happening is that in scaling phenomena, the system, depending on where it starts from, what kind of initial condition you impose, and what you choose as your origin of time on your clock, picks up dynamically this T star. So this T star is not something that you can explain in the language of the scaling itself. Is an external parameter that comes from initial condition, and it's going to be picked over and over again depending on the initial condition you start with. Yeah, of course. Trev is a timescale that you introduce to make this ratio dimensionless. In practical terms, you might think of this as setting a timescale that sets the variable that sets the overall energy density. Like that's a natural way to think about it, right? With energy density being like 1 over the time to the 4th power in natural units, right? Yeah. So it's like a sort of like amplitude variable, right? Yeah. And of course, like when you look at this expression, you can write this expression as some time-dependent scaling exponent, right? You can just write this expression as t to the power beta of t. But the whole point that I want to make is that this prescaling, the time dependence of the scaling exponent, is nothing else than just offsetting the time variable. So that it's scaling with time offset time variable that is required because self-similarity wants to pick the notion of its origin in time. So this is you can ask a high school student to solve this equation and come to this conclusion, right? So it's like an extremely simple thing to do. But the beautiful thing about it is that about half a year after our work was done, a paper appeared by a cold atom lab in Cambridge, led by Zoran Hadibabic, which precisely saw this effect in a cold atom experiment. So the self-similar behavior in time that they observe is, I mean, for these plots, for the other cascade, it's a cascade to the infrared associated with the particle number, but the principles are the same. And what they see is that when they start with an overoccupied initial condition, and you look at the distribution function at various times as a function of momentum. I mean, this is roughly speaking the shape. If they introduce this T star that they fit to every initial condition, it turns out that all these plots fall onto each other, giving rise to a single form of Fs. Had you not introduced this T star, unless you are at very late times, that would make some spread in this plot, right? So that's an observation that this T star is really a deal for non-thermal fixed points. It extends non-thermal fixed points to earlier times, and that was a very beautiful experience for me, because I've been working on things that are much harder than this without making any experimental direct impact. And here, like, offsetting time by a constant, solving a simple ODE is something that made an experimental impact. So, I mean, it's a very mindset changing experience. Yes. Yes. Well, I mean, like, there's a good. There's also a question over which range of times the non-thermal fixed point is valid, right? And of course, before you're gonna reach, you're gonna have some other type of dynamics, right? So I guess like the question that you're asking is like this place where B vanishes, like within the range where you trust non-thermal fixed point, and I think like typically the answer is no, because there's other stuff that comes on top of it. Yeah. Anything else? No. Okay. So some comments. Um, so non-thermal fixed points are things that are defined by overoccupation and dimensionality reductions and are observed for weakly coupled systems described in this case by the Boltzmann equation. This notion of prescaling is a direct consequence of the equations of motion. And the prescaling exhausts the dimensionally reduced ansatz. So like when you assume this factorization of the distribution function, there is not more that can happen. Prescaling is the only answer. And at this level, although the motivation was interesting, the prescaling does not seem to have much to do with hydrodynamics. And later in the talk, you will see that prescaling does not originate from a hydrodynamic quasi-normal mode. It originates from a transient quasi-normal mode. Yeah. Any questions, comments, thoughts? Yes. No, I think it's a very good question. I think that's one of the questions that motivates my interest here, like how much you can push it. I think as of now, to the best of my understanding, the statement that I could make that I would feel satisfied with is that within the realm of weakly coupled systems described by Boltzmann equation, there's going to be some subsets that are going to give rise to this self-similar behavior in time. Weak coupling is needed because you can introduce perturbative corrections to your scattering dynamics that you associate with the collision kernel, and then that would introduce other powers of f, right? So as a result, like that would like going to higher orders in weak coupling would not necessarily be compatible with taking the amplitude of f to be very large, right? Because you might be picking like higher order, keep like next order term, next to leading order term, and so on and so forth. So I feel like you need like really to have weak coupling to be able to do this. So I feel like this is the statement as of now. But you can be more creative. You can ask like, is it possible to get from strongly coupled dynamics observables that follow this kind of a pattern? And then would you be able to call them holographic non-thermal fixed point? And that's something that we're thinking about in Ghent, but we don't have yet anything concrete to say. Yeah. I think in this case, like you probably need to adjust over occupation and weak coupling. So like, okay, I'm like the Villar, I mean like then you just have. Well, I'm not sure. Let's see. Highly occupied state. You have to allow for high. Okay, I mean within the consistency of your description, you have to allow for highly occupied state. I feel like that's the statement. Yeah. No, I did have to make approximations. Yeah. Oh. But but I feel like the power of F like would do it, right? Like the question is, can you in within this description, can you consistently drive occupation high, right? And if you cannot do this, I mean, mathematically speaking, you can probably, right? So you can mathematically speaking, you can solve the equation within this ansatz. But physically speaking, maybe this equation breaks down before, as a physical description before you do this, right? Yeah, exactly. Yes. Yeah. I see. Yeah, that's a good question. Yeah, I'm like, in principle, I mean, naively speaking, live here, it seems you should be able to play this game, right? The only thing that, yeah, I feel like in this case, you should be able to play this game. Yeah, but when you're over occupied, right? Like the no, but like this is no, but this is different. No. No, that's a good point. I mean, mathematically speaking, I would say it should go through. Physically speaking, I'm not sure if this would be consistent, but like that comes to Gabriel's point. But I think like we should discuss this because that does not affect the content of my talk. We should discuss it afterwards during lunch. Yeah. Okay. Yeah. So of course, like the interesting outcome of this discussion is it will be very nice to have a more thorough understanding of classification of non-thermal fixed points. Like what are the necessary ingredients for them to have it? Because so far we have like basically evidence in concrete cases of collision kernels that are relevant for high energy physics or cold atoms. Yeah. So now I want to, in the last few minutes, I want to talk about quasi-normal modes of non-thermal fixed points. So when you talk about quasi-normal modes, this is related to the Fourier decomposition of your signal. And in order for the Fourier decomposition of your signal to be really useful, you want to do this on top of a static background, right? So naively, you might think, okay, the non-thermal fixed point is not static, so you're cooked. But there's a sense in which non-thermal fixed point is static because there's like this dependence on momenta that is static, right? So if you take this as sort of like your reference reference point in the analysis, then the notion of a quasi-normal mode approach to this should make a perfect sense. And this is something that we started exploring when Mathis Delescluze was still a master student at Ghent. And what we did is like we took the Fokker-Planck kinetic theory. The reason being that is like the simplest kinetic theory that I could think of. That, but maybe there are simpler ones that give rise to non-thermal fixed points. And we started with the scaling ansatz, and then we wanted to understand what Boltzmann equation would imply for the presence of naively exponentially suppressed terms on top of the scaling ansatz. And it turns out that if you do the math generally for any Boltzmann equation that gives rise to a non-thermal fixed point, it turns out that stuff that comes on top of the scaling function is not really exponentially suppressed, but it's actually power law suppressed, where the power law is in principle a complex exponent that's going to be the eigenvalue in your quasi-normal mode problem. So now the quasi-normal modes on top of non-thermal fixed points are not exponentially decaying as they were in holography, but are going to be power law suppressed contributions that come on top of the scaling function, right? And of course, what you observe in numerical simulations as well as in cold atom experiments is that non-thermal fixed points are approached, right? Like that it's possible to reach them. As a result, like it's unlikely from this perspective that they would have unstable directions, right? So what you would like to demand is that these omegas lie in a lower half plane, right? That reflects the stability of your system. And indeed, what we did is we implemented the eigenvalue problem for these omegas for the Fokker-Planck Boltzmann equation. And this is the picture that we got for the lowest lying 4 modes. So there is a mode that is exactly a 0 mode. And then we found 3 more modes and further ones that are still numerically unstable. So like I don't show them because there's a lot of noise in them. And I believe like it's possible that actually there are infinitely many quasi-normal modes extending all the way to infinite frequencies. Lying on, here in this case, lying on the imaginary axis. This one is at -1. And these ones are at some numerical values that could well be irrational numbers, right? So this is the Fokker-Planck result. And if you compare, this is the picture that you see in holography. So in holography, the quasi-normal modes appear as associated with an exponential behavior. For non-thermal fixed point, they're associated with a power law approach. But the picture is that if you go to 0 spatial momentum, to homogeneity, the hydro ones appear as a 0 mode, and then like these ones appear as transient ones. So of course, what you would like to understand is these ones as transient ones. And then we do some analysis for the first time, and when you do some analysis for the first time, it's important to have some cross-check, right? Because, well, I mean, you never know if you're doing something that is reasonable or not. And it turns out that there's a very nice cross-check that you can do. So like all these modes that I show here are generated numerically in a similar way in which you solve for quasi-normal modes of a black hole in ADS. We use the pseudospectral method. I mean, the experts know what I'm talking about. For the rest, it's not very important. And then, like, what we get from this method are these eigenvalues that we want to see converge with respect to number of points that we use in the momentum direction and numerical accuracy and all sorts of these things. And we also get eigenfunctions, so like the profile of momentum dependence of the associated perturbations, so like these things. And then when we look at the left-hand side, on the left-hand side, we see actually two parameters. And sorry for changing the notation. We see like what I previously called Tref, now I call it T0, it's the same variable. And we also have like this T star offset associated with choosing the origin of time, right? And these two are parameters with which we can vary our distribution function. So what we can consider is a small variation in T star or a small variation in T naught. And as a result, when you Taylor expand it, what you're gonna get is you're gonna get a contribution to the signal that looks precisely like this ansatz. So indeed, like what you should expect that 2 out of these quasi-normal modes that you get should originate from varying either with respect to T naught or varying with respect to T star. And indeed, this is the case. So over here, what I'm showing for you are the momentum dependence of the two quasi-normal modes, one associated with the 0 eigenvalue, so the 0 mode, and one associated with -1 eigenvalue. And what I'm overlaying here is the momentum dependence that you obtain if you make a variation with respect to T naught, so Tref, and over here, when you make a variation with respect to T star. And what you see is that the result that is numerically predicted follows up to numerical error extremely much on top of the prediction coming from linearizing in these parameters, right? So that's a non-trivial cross-check that the numerical analysis that we did actually produces physics. It's not just garbage. So in a sense, like these quasi-normal modes were seen in experiment because this quasi-normal mode is associated with variation in T star, and T star is nothing else than this notion of prescaling, and prescaling was observed in experiment, right? So like you might think about going from here to there as introducing this quasi-normal mode that is associated with the eigenfrequency -I. And there's a puzzle in this picture because this prescaling seems to work very nicely. And it would be extremely natural to think about the prescaling quasi-normal mode as the one that is the lowest lying transient one. But somehow it's not entirely the case. There's also in the setup this mode and that mode that appear that are less decaying. So it will be very interesting to understand why this is the case. Because one possibility is that if you look at the signal analysis for the Fokker-Planck kinetic theory that is subject of this investigation, you would not see a clean prescaling because of the presence of this and that mode. And that would indicate that the eigenmode spectrum in this experimental example that they tested is different and has a prescaling mode as the lowest lying transient one. And when making all these comments, I'm directly referring to the holographic intuition, right? Where what we expect is if we wait long enough, is that it's going to be the lowest lying transient quasi-normal mode that's going to be contributing to the signal. Any questions, comments, thoughts? Yeah. Yes, I think this equation is conformal, yeah. No, I will have to check. I don't remember. No. But we can talk about it later. Yeah. Anything else? No. Okay. So of course, we saw this picture earlier in the talk where you see the hydrodynamic modes in holography. And as you take the spatial momentum to 0, like they all go to the origin. And we have this picture where there is a zero mode length here, but the analysis was done in pure spatial homogeneity, so no external momentum. So now the idea of this upcoming paper is that if you add a spatial momentum to the system, this zero mode, what it should do is to split and give rise to hydrodynamic excitations, to the shear excitation and to the sound mode excitation. And indeed, we do see such a feature, but we observe it using a different framework. We don't calculate the quasinormal mode in the presence of external momentum directly. What we do is we use the 14-moment approximation, and we start with the isotropic distribution function. We consider a small perturbation. We write this small perturbation in a Taylor expansion in particle momenta, and use truncated low moment expansion of the Boltzmann equation to close the system of equation and obtain an equation of motion of the MIS DNMR type for pi mu nu. And after the dust settles, what we obtain for 2-2 scattering is this kind of an equation that many of you are familiar with. But now remember that our point of departure is intrinsically time dependent. I mean, in our system, the energy and the energy momentum tensor of the background of the non-thermal fixed point is exactly the same as in equilibrium. It's constant energy density, constant pressures. But the distribution function that gives rise to this behavior is intrinsically time dependent. And as a result, the transport coefficients of the shear viscosity and the relaxation time, they come intrinsically time dependent. And they happen to scale linearly with time. And there's a cross-check that you can do. As you know, like this kind of an equation, when you linearize in the presence of spatial homogeneity, I mean in spatial homogeneity, should give rise to homogeneous isotropization kind of a dynamics. And what we show here is the predictions of the behavior for the pressure anisotropy versus time, and indeed these two qualitatively match. And this should be compared with the earlier result for quasinormal modes. So these quasinormal modes were isotropic. Over here, we secretly talk about anisotropic quasinormal mode because we introduced the pressure anisotropy, but the qualitative behavior is exactly of this type, which is the parallel decay. And then there's like something interesting that I want to discuss as last part of my talk, which is that we have a novel form of hydrodynamic behavior, which is defined on top of a far from equilibrium state. And as a result, we have time-dependent transport coefficients, far from equilibrium transport coefficients. And one thing that you can think is, we have this far from equilibrium liquid. How can we compare it to other near equilibrium liquids that we know? For example, to the liquid of the same kinetic theory, but near equilibrium, or to holography. And one thing that we learned throughout history also, due to Pavel, Son, and Andrei Starinets, is that a nice thing to consider for near equilibrium liquids is eta over S, right? Because this introduces a hierarchy between strongly coupled systems and weakly coupled systems, and moreover is universal in holography in the two derivative limit. But it turns out that if you take this system, the far from equilibrium liquid that we consider, and you consider the eta over S ratio, it's not very insightful. It retains time dependence. And as a result, it's rather hard to compare to near equilibrium liquids in which this ratio is just some number. So one idea that we had is to consider another ratio that might be insightful. And this ratio is a ratio of the shear viscosity to the relaxation time understood as the decay rate associated with your system times the energy density. And it turns out that when you take this ratio, what you get for our kinetic theory system is 4/15 and this is the value that is both relevant for non-thermal fixed point and equilibrium. And if you apply this, the same kind of quantity to holography, where the relaxation time is going to be basically the gap in the quasi-normal spectrum in holographic models that is of the order of temperature times 2 pi or something like this, then the ratio that you get is of the order of 2/3, right? So these two quantities are actually quite close to each other. So that's some fruit for thought, because it's like a new kind of a ratio, new old kind of a ratio that you can consider in this kind of systems. And last thing that I want to say before lunch is that non-thermal fixed points so far have been studied under the assumption of spatial homogeneity. And this kind of an equation that we derived allows to model, to introduce a notion of an inhomogeneous non-thermal fixed point and open a wealth of new experimental phenomena, such as elliptic flow, for example, for non-thermal fixed point and these kind of things. So since I also run over time and we have lunch, let me just display the summary, and thank you for your attention. This one, yeah. For holography, yes. Yeah, over here, we didn't check that. We don't know yet. That's an expectation. No. What I mean is that there are modes whose frequencies do not converge yet for the values of the parameters that we use in our simulations. So we would have to take like more grid points, increase accuracy, and this gets more and more numerically costly. Yes, I mean, like, there's a way to test if there are there's a way to test, like, I feel like it's natural to expect that there's going to be infinitely many modes. What's more interesting is, does the spectrum continue to, infinity or not? And there's a way to do this, like you can do WKB approximation as people have done in holography. I'm not sure who did it. Maybe Lubos Model actually did it at some point, maybe somebody else. So you can try to do WKB here for large n. I'm like the identification number of the mode, and in this way try to see, like, where these eigenfrequencies would settle on, right? We haven't done this analysis. It would be interesting to do it. No, these we already found. Like, I mean, like, this is the mode that originates from variation with respect to Tref, T0 here, and this one is the one that originates from variation with respect to T star. So we don't expect any other modes of special features like this, because we exhausted the parameters that we have in our description. Yeah, thank you for the question. Oh yeah. Yeah. Yeah, T0. Well, yeah, you can think about T0 as a fitting parameter. Yeah. They have different meanings. So T star, sorry, T0 Tref is the same. I'm like, it's just my my error of not being consistent throughout the presentation. But the meaning of it is that if you're assuming the scaling ansatz and you calculate the total energy density, this total energy density is going to be related to Tref. So by varying Tref, you vary the total energy density or particle number. And as a result, in your experiment, like, you only deposit some number of some value of energy or some number of particles, right? So what you should do is to fit this to the experimental data. No. I'm like, the tau pi is gonna good. Yeah, this good. These timescales are gonna propagate into tau pi. Yes. Yeah. Yes. Yes. That's something that I think is only partly understood. It would be interesting to understand this better. Um, so there are two kinds of non-thermal fixed points. One associated with the UV cascade and one associated with the IR cascade. So the UV cascade is something that I mostly focus on in my theoretical studies. And there, what happens is that the amplitude of the distribution, the power of the associated with the amplitude scaling. So for example, here, this power alpha turns out to be negative. So for QCD, it's like minus 4/7, basically minus a half. So what happens is that the amplitude of F in the scaling regime drops steadily, right? And remember that you derive non-thermal fixed points from this more complete kinetic theory by the virtue of the assumption of overoccupation. But this overoccupation, if you have it initially, it's not going to last forever, even if you reach the scaling regime, because in the scaling regime, the overall amplitude drops in a parallel manner. And at some point, you need to start including the effects in the Boltzmann equation that you neglected, right, by the virtue of the Taylor expansion, right? And then when these effects become non-negligible, that's when you exit non-thermal fixed point. But the thing is that this is a parallel effect, so it's like a very slow effect, and you have to really wait for long till you reach this regime, right? So it's not something that is easily seeable in simulations. Now, for the IR fixed point, what happens is that you seem to be forming a condensate in a sense that everything seems to be sort of shrunk to the zero momentum because it's an IR cascade, and at some point, I think you really get like a macroscopic coherences in your system. Yeah. Yes. So I feel like there's I mean, okay, this is something that I haven't thought about very much, but empirically speaking, you can take the full QCD kinetic theory and solve for non-thermal fixed point. This kinetic theory also has like 1-to-2 scattering associated with the presence of the medium, and there like it's also very prolonged effect, this non-thermal fixed point, right? So but indeed, like the dynamics is dominated by small angle scatterings. So it might be that this is one of the reasons, maybe like even the key reason why it's not faster. I guess like the interesting way of turning your question around would be, how to, for what kinetic theories like these things, do not materialize or become very short-lived, right? Um, what I saw in my studies is that like this assumption of overoccupation like literally gives rise to this gives rise to this kind of a behavior, and then from this follows this parallel approach, right? So somehow I don't see how to get something faster, because faster would mean probably exponential, right? Like I have no clue how to get it from Boltzmann equation. But this is something that maybe we can discuss here at the workshop. Yeah. Yeah. Thanks. I mean, interesting thoughts. I wish I had something to say. Oh yeah. 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 This one. Yeah. Which ratio? Like this one or that one? Yeah. But apparently not, because like this ratio, weak coupling. Yeah, yeah. Yeah, it's like tau pi is of the order of the inverse of the temperature in holography. And and basically you can write it as eta over s times tau pi times t. So tau pi times t is like order one number. Eta over s is 1/4 pi, and this is how you get this estimate. Unless I'm like, it's not much different. I mean, I might have made some factor of 2 mistake yesterday evening, but I think it's roughly correct. I mean, the one appearing here, yes, is like your eta. Over here, the eta is this thing that. Oh, that I'm not sure. I'm like, I haven't thought about it in terms of Kubo formula, but I mean, at the level of the derivative expansion of the energy momentum tensor around non-thermal fixed point, I mean, like it would appear as a shear term. Yes. Yeah, yeah. So this is what I mean by, I mean, myself and hopefully Gabriel as well, as eta. Yeah. Oh, you mean like the causality bounds and things like that? Yeah, 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 sure, sure. But I didn't want to get to this kind of discussions. Yeah, yeah, yeah. Yeah. Yeah, if you look at MIS type equations, indeed, like eta over tau pi is something that is important, right? You cannot make tau pi too short, right? Thank you.